Getting more on super Riemann surfaces a little bit. So last time we found that on any complex supermanifold, we can define periods of a holomorphic section of the Berezinian. What? But I want to start today by explaining that for X, a super Riemann surface, which means in particular dimension 1, 1, there's another definition of periods. Well, so to a certain extent, we'll say something that would make sense on any complex supermanifold, but the equivalence to the construction involving the Berezinian is special to super Riemann surfaces. And this will be, I think, related to what Pierre was telling us. So remember that a super Riemann surface is characterized by having a subbundle of the tangent bundle, which in local coordinates d theta is generated D is generated by this nice vector field that's given by that formula in local coordinates. And it fits in an exact sequence where the quotient is naturally isomorphic to d squared, because complete non-integrability means that d theta and d theta squared give everywhere a basis of the tangent bundle. In other words, d theta squared is an even vector field that's required to be independent of d theta, so together they give a basis. And if d theta is a section of curly d, then d theta squared is a section of d squared. So we have this kind of structure. And of course, we also have the dual exact sequence. T is Tx, where x is a super Riemann surface. T star x is the cotangent bundle. And also, you heard earlier today that the Berezinian of x is D inverse, I hope. So there's a map from T star x to the Berezinian. So if you like, it maps a 1 form, which is a section of T star x, to a section of the Berezinian. And, well, we can calculate, describe this in local coordinates. So d minus 2 corresponds to the kernel of this vector field d theta. So d minus 2 is the subbundle of the cotangent bundle generated by dz minus theta d theta. And then we identify d inverse as the cotangent bundle mod d minus 2. Well, the coefficient of dz is 1, so reducing by d minus 2 can mean forgetting dz. So we can think of d inverse as being generated by d theta modulo this guy. So the isomorphism, so when we make this isomorphism between the Berezinian and d inverse, we identify d inverse as being generated by d theta modulo dz minus theta d theta. And the isomorphism just maps d theta to the section of the Berezinian, dz slash d theta. That's what you will learn if you unwind Pierre's explanation of this morning for why it's true that the Berezinian is isomorphic to D inverse. So concretely, we can map a 1 form to a section of the Berezinian. So if lambda, which is a of z slash theta dz plus b of z slash theta d theta is a one form. How do we map it to a section of the Berezinian? Well, we're supposed to get rid of dz by reducing mod. We're supposed to reduce mod dz minus theta d theta, which is to say we're supposed to set dz equal to theta d theta. So we just replace dz with theta d theta. Lambda maps to a of z theta times theta d theta plus b of z theta d theta. But as a section of the Berezinian, d theta corresponds to dz slash d theta. So concretely, that's the map from a holomorphic one form to a section of the Berezinian. Now, that map is, of course, not injective. Or hardly can be, because the cotangent bundle had rank 1/1, and the Berezinian had rank 1. So there's a kernel in this map. But there's something really fun, which I imagine can be better explained with what Pierre was saying before, but I learned it from a paper of Rosley, Voronov, and Schwartz. Well, I recommend two papers from Rosley, Voronov, and Schwartz from about 1987, who showed the following. So this map is an isomorphic. So if we require d lambda equals 0, then the map to the Berezinian becomes an isomorphism. Let's just try it. So we write lambda is a of z and theta dz plus b of z and theta d theta. And let's concretely try to impose the condition that d lambda equals 0. First of all, d lambda is going to be a holomorphic 2 form. But unlike an ordinary Riemann surface, on a super Riemann surface, a holomorphic 2 form isn't 0, because remember, we will have dz d theta, and we'll also have d theta squared. So in particular, when we calculate d lambda, we're going to get d theta squared will come from only one place, the derivative of b with respect to theta. So that has to be 0, and then to make lambda closed. And then dz d theta will get twice. I think we'll get d theta a plus dz b. Possibly with the wrong sign. I didn't, on the fly, work out that sign. So we learned two conditions. One is that d theta b is 0. And then we get a condition that expresses d theta a in terms of the derivative of b. So that can be summarized as the statement that a closed holomorphic one form is lambda equals f of z dz, which of course is closed. There's no thetas in sight, so just like in an ordinary Riemann surface, one form is closed, plus an exact form, d of theta times b of z. That's the general that's the general local expression for a closed holomorphic one form. And now, when we map to a section of the Berezinian, as we did before, magically, we're going to find I think we get b of z plus theta times g of z. But magically, it's now an isomorphism. So there were absolutely no global considerations. This was a purely local calculation. Well, yes. The way that the theta came in is that, remember, when we reduced the formula, when we reduced modulo dz minus theta d theta, dz turned into theta d theta.
Well, you still have the expression for lambda in terms of a and b, and now you told me what a and b are. So
yes,
compare.
right. Yes. So when we worked out this formula, a and b had an arbitrary dependence on theta. But now we've restricted it to the case where lambda is closed, which tells us what kind of dependence on theta we need, such that it can be written this way. And then you'll now find out that the map from closed holomorphic one forms to sections of the Berezinian is 1-to-1. It's just locally 1-to-1, no global considerations. So that tells us we could calculate periods in a more naive way. So if we're given our section of the Berezinian, which locally looks like this, there's a corresponding closed holomorphic one form, lambda. And now we would compute its periods in a slightly more naive fashion. If we're given a one cycle in the corresponding reduced space, where we've set to 0 any odd parameters on which x might depend, not canonically, but topologically, we can lift a one cycle in the reduced space to a one cycle in x. And then because lambda is closed, we simply take the period of lambda over that one cycle. So we made that kind of argument yesterday. Any questions on that?
What cycles have periods in a general complex manifold?
Middle dimensional cycles. I'm not sure precisely what if you're just asking what the question sounded like.
Yeah.
In general, on a complex manifold, or in a middle dimensional cycle, you might expect that some holomorphic form will have a non-zero period. And we're in a similar situation here. Topologically, our one cycles correspond to one cycles in the reduced space. The only major difference is that closed holomorphic forms will still have periods, and therefore they have classes in the ordinary cohomology, but those classes are not of the usual Hodge type.
A one cycle in X is a submanifold of dimension 1, 0?
Yes. So I perhaps should have spelled that out better. Lambda was a one form, so what it could be integrated on is a manifold of dimension 1, 0. And the way we find them is that we literally take a manifold of dimension 1, 0 in the base, and we lift it somehow to the total space. There's no obstruction because of an argument similar to what I gave yesterday. If you like, well, since everything is infinitesimal, there's no obstruction. X is an infinitesimal thickening of X reduced. So you have to explain what you want to do in some infinitesimal directions, but you don't have to move very far. There's no room for a topological problem.
The universal covering, you can really integrate the form and then you see what happens if you go from one field.
Yes.
Like this.
Yeah. Although, had we been in complex dimension n, we wouldn't have that argument. But here we could go to the universal cover, and we just integrate from a point to its.
By linear relation? Or?
We will discuss the Riemann bilinear relation soon. So how many sections of the Berezinian of X are there? Or equivalently, how many closed holomorphic one forms? Well, is there a question I can answer? No? Okay. Well, the formula I think I called it B before, gives an answer that if X is split, well, then f of z dz is an ordinary one form on the reduced space, and B of z is a section over the reduced space of k to the 1/2. So, well, you see, if X is split, the periods of the one forms that are pulled back from the reduced space are going to be the same as they were before pulling them back. Because if X is split, we could simply take the cycle gamma to be a classical cycle in the reduced space. On the other hand, an exact form has vanishing periods. So if X is split, if there are any extra one forms, they have vanishing periods. And the one forms that are pulled back from the base have their classical periods. When we go away from the split case, the theory is better if we assume that H0 is 0. You'll see in a moment, actually Pierre mentioned this condition this morning, but you'll see in a moment why that makes our life simpler. So we're going to then assume for a little while an even spin structure. The importance of an even spin structure is that it's impossible for this H0 to be 0. Well, see, if we had an odd spin structure, then there would be an extra odd holomorphic differential. I believe it disappears under small perturbations away from the split locus. And that's extremely inconvenient. So
Computed, or
that it disappears?
that's the thing,
It can be, which,
that H0, that one. That
this is an ordinary Riemann surface. So it's part of classical algebraic geometry to describe H0 of x and k to the 1/2. So for an even spin structure, it's generically 0. And for an odd spin structure, it's generically one-dimensional. I'd prefer to discuss the case of an even spin structure when there are some nice things to say that don't have such simple analogs as for an odd spin structure. So for a little while, the spin structure will be even and will be away from the locus, which is called the theta divisor in classical algebraic geometry, where this becomes non-zero. So we assume that H0 of k to the 1/2 is 0, and that
Maybe it was theta null.
this is called the vanishing theta null.
Fine, it's set. It's
Yeah,
not
it's
It's fine because the point must be over the
It's
two.
called the theta null divisor.
Yeah, theta null.
I said theta divisor.
Yes, okay.
Now, our condition is equivalent to saying that H0 of x with values in O is isomorphic to C. I should better say, well, for the moment in the split case. We'll have that in a moment without the split case, but for the moment in the split case, the even sections of O we know can only be constants, and our hypothesis exactly said that there were no odd sections. And we and then in the split case, it's also true that H1 of x and O has dimension g/0. Well, see, the odd part of that would be H1 of x and k to the 1/2. But that's 0 by Serre duality with H0 of x, and this is x reduced. And k to the 1/2 here with our hypothesis. So the odd part is 0, and the even part is just the classical thing. Now, if we deform away from the split locus, well, cohomology can't jump upwards. But in this situation, it can't jump downwards either, because we're not going to lose the constant section. And by Riemann-Roch, if H0 is locally free, H1 will have to be locally free. So as long as we keep away from the theta null divisor, the cohomology of X with values in O is locally free. And by Serre duality, which unfortunately we haven't explained properly. I don't know if Pierre plans to explain it. Okay. Okay. Well, there's an analog of Serre duality for ordinary supermanifolds, which here would say that the cohomology with values in O is dual to the cohomology with values in the Berezinian. You can actually imitate classical proofs of Serre duality, I think. So therefore, this is locally free. But the case of that I wanted to use was just that H naught is locally free. So the sections of the Berezinian we had in the split case aren't going to disappear when we go away from the split case. Yes?
The role of the dualizing?
Yes. So, as in the case of the dualizing sheaf of a complex manifold, it can be a section of the Berezinian can be integrated on a middle dimensional period, middle dimensional cycle. But part of what makes the dualizing sheaf have that property is that in an n-dimensional complex manifold, an n form, a zero n form valued in K, can be integrated in the ordinary sense. And that also has an analog here. The only trouble is that we'd have to first explain what the concepts mean. Because as we've set it up, there isn't a canonical smooth model of X. But we'd pick a smooth model, and then we'd imitate the classical theory. And, well, an awful lot of statements have analogs. So, you see, we explicitly saw that in the split case, for genus G, there's a G-dimensional space of sections of the Berezinian and therefore closed holomorphic one forms. And the point of this discussion here was to make sure that none of them disappear when we go away from the split locus. Remember, in general, cohomology can jump downward under a small perturbation. And without this assumption, that would have happened. Without this assumption, we would have had extra closed holomorphic one forms that would tend to disappear under infinitesimal perturbation. But under this generic assumption, things are locally free. So on our super Riemann surface, by the way, I'm going to continue with arguments that essentially follow Rosalie, Voronov, and Schwartz from the 80s. Although, given time, I believe Pierre would give other explanations. So, so on our super Riemann surface, we have a full set, let's say, of genus G of, well, closed holomorphic one forms by full set, I just mean there are as many of them as there would have been classically. And so we can define a period matrix. So, well, as in the classical theory, one way to proceed is to pick a basis of A cycles. That's a maximal null a basis for a maximal null subspace of the first homology, and a corresponding basis of B cycles. And I pick the lambda I such that
Of cycles on X reduced.
if you wish, yes, you pick classical A and B cycles in the reduced space and you lift them somehow to X. Doesn't matter exactly how you lift them to X. You pick the lambdas so that the integral over the A cycle of lambda J is delta Ij. So how do we know we can do that? We know it because we could do it classically. And therefore, if you turn on odd moduli, you've only made a tiny mistake. You have to invert a matrix of the form 1 plus something nilpotent in order to make the lambdas do that. And then you define period matrix as the integral over a B cycle of lambda I. And I was already asked, in effect, whether the period matrix is symmetric. But we had to hold off on until we had time to define it. So the claim is that, so by the way, up to a point you could do this for a more general complex supermanifold. But the period matrix would not be symmetric. But the claim is here, for a super Riemann surface, the period matrix is symmetric. I believe the analog for a 1-1 supercurve that isn't a super Riemann surface, this morning Deline explained the duality between x and x prime, where they parameterize divisors in each other. And the transpose of the period matrix of one should be the period matrix of the other. In fact, Deline was sketching a proof the other day. But for a super Riemann surface, we will prove the symmetry of the period matrix. So a super Riemann surface therefore has a Jacobian, which is a principally polarized abelian variety. It'll be a principally polarized abelian variety that in general doesn't obey the Schottky relations. So when you get to genus 4 and higher, where there are Schottky relations, it won't obey the Schottky relations. It's also only generically defined, because we needed a condition well, first we needed an even spin structure, but more than that, we needed to be away from the theta null divisor. So there's a divisor on which this definition is bad, but away from that definition, we'll have a principally polarized abelian variety. So we should remember the classical proof. The classical proof, you say that if lambda I and lambda j are holomorphic 1 forms, then lambda I wedge lambda j is 0. So 0 is equal to the integral over, I'll write x0 for a classical Riemann surface. I don't want to call it x reduced because I'd prefer to write the classical theory without talking about super Riemann surfaces. But then topologically, the integral over the whole surface of the product of two 1 forms can be written in terms of the cohomology classes of the 1 forms, or equivalently in terms of their integrals over A and B cycles. Let's call it lambda and lambda prime to not have too many indices. So one has this Riemann bilinear relation, and if we normalize the 1 forms to have canonical A periods, and define the period matrix in the classical way, then this formula will tell us that the period matrix is symmetric. Okay. So obviously we have a slight problem in imitating this because on a super Riemann surface, a holomorphic 2-0 form isn't 0. But RS and V got around it as follows. They showed that a closed holomorphic 2 form, theta, let's say, on a super Riemann surface is exact. Okay, well, that's the first step. So there are a couple of steps to okay. So theta is d lambda for some lambda. I'll explain how to prove that in a moment.
Compute the form of a closed. No, 1 form. Sorry, never mind.
A closed holomorphic 2 form
Yeah, I can't read.
is exact.
Yeah, okay.
So we'll prove it. So now it's not true in a general 1-1 complex supermanifold. There are elementary counterexamples. In fact, it's a good exercise to find one. You're allowed to do that exercise by hunting in my papers where I gave an example, because in order to do that, you'd have to probably learn a bunch of things about super Riemann surfaces. I won't tell you where you'd find it. But anyway, this is not a statement about 1-1 supermanifolds, but it's for super Riemann surfaces. A closed holomorphic 2 form is exact. We'll prove it in a moment, but we'll explain how to use it as follows. So we're going to have the fact that lambda wedge lambda prime is d of capital lambda, and we want to integrate that somewhere to say that so where are we planning to integrate that? Well, all we can, lambda wedge lambda prime is a 2 form, so all we can integrate it over is a manifold of dimension, an ordinary bosonic manifold of dimension 2/0. Which you can think of as a smooth embedding of x reduced in x. So if x is split, then x reduced is canonically embedded in x. If x isn't split, it can't be embedded in x holomorphically, but it can still be embedded in x smoothly. I'd like to remark that since x reduced is an ordinary complex manifold, we know what are smooth functions on x reduced. And to say that there's a smooth embedding of x reduced in x just means that holomorphic functions on x pull back to smooth functions on x reduced. So the statement made sense. And there's no problem with it. Sorry. If x is defined over a point, there's always an embedding. But that case of what we're discussing would be trivial. We're actually working over a parameter space. And when we make this discussion, we don't want to set to 0 the parameters. So we're working over a ring, C of alpha 1 up to alpha s, where the alphas are odd parameters. If we set the alphas to 0, our discussion would become vacuous. So we don't want to set the alphas to 0. We treat them as constants. So that being so, there's no embedding of... see, we can't define x reduced without setting the alphas to 0. That's the basic problem. So in x reduced is a purely bosonic manifold. But because x depends on the alphas, it's not true that we've got an embedding of x reduced in x holomorphically. But there's no problem with the smooth embedding. There was such an embedding when the alphas were 0. And turning on odd parameters is never going to change any statement of a topological nature. So let's call that embedding S. So we do this integration over S of x reduced. And having learned that the integral of lambda wedge lambda prime is 0, we then have the classical argument. X reduced is an ordinary Riemann surface. So we just make this argument, and it shows the symmetry of the period matrix. Any questions on that?
It uses the statement that you take x as some infinity variety, you add those alpha 1, alpha s to it, and this you map to x, but alpha corresponding to alphas.
Yes. And that we cannot do that holomorphically.
No.
But in the usual way, we can do it smoothly. What that means is locally we could even do it holomorphically, but we couldn't fix it because we would run into a sheaf cohomology group that would be non-trivial. The obstruction would be non-trivial in holomorphic sheaf cohomology, but in smooth sheaf cohomology, it's trivial. Any questions?
Is not parameterized by odd parameters. I'm confused. Why isn't just reduction mod nilpotence automatically giving you this?
We take x reduced and then we tend to multiply by spec C of alpha mole.
Oh.
Well, the problem here is that the way I said it at the beginning is more the way most physicists would tend to think of it. this depends, x depends on the alphas, but we think of x reduced as not depending on them. Sorry. Okay. Yeah. Well, the forms that we're trying to integrate do depend on the alphas. So although you can think of x reduced as not depending on the alphas, when we make its embedding by s, and then I should have written this as s star of lambda and s star of lambda prime. And this would be s star of d lambda. And then I would have said that it was d of s star of lambda. And that would be 0. But anyway, we can't avoid the fact that s star of lambda depends on the odd moduli because lambda does. I think that way of stating the argument is closer to the way most physicists would think about it. Any other questions?
Are you contrasting reducing it all the way or fiber by fiber
You
reduction?
cannot reduce fiber by fiber.
Yeah, as Pierre says, we can't reduce fiber by fiber because we can't set the thetas to 0 without setting the alphas to 0. The reason we can't is that in constructing the supermanifold, coordinate changes like theta going to theta plus alpha were made. In other words, what's called theta in one coordinate patch is called theta plus alpha in another coordinate patch. So we cannot consistently set theta to 0 without setting alpha to 0. That's what leads to the subtlety of supermanifold theory. Otherwise, supermanifold theory would be kind of trivial. So all I was trying to do here, the reason there isn't such subtlety here is that I was just trying to map in an ordinary bosonic Riemann surface. And we only cared about it topologically in that argument. So we could be crude. We start with x reduced, if you want, where we set everything to 0. And then
So just the topological Riemann surface, and you integrate on the topological Riemann surface.
we have to explain what we integrate. But we map x reduced smoothly to x.
Yeah, okay.
And then we pull back lambda and lambda prime, use the fact that their wedge product is exact. So the pullback of the wedge product is exact. And finally, this is 0. And having learned that, then we can make the same argument as before with s of x reduced here. And we learn that the period matrix is symmetric. But there's one step which I haven't justified yet, which is that I said that a closed holomorphic 2 form is exact. And actually, there's a fun local formula. So the proof doesn't involve any global considerations. There's a purely local formula given a closed holomorphic 2 form to write it as d over 1 form. So again, that formula is due to Rs and V. So we're going to look at a couple times at this exact sequence. So in particular, we have a map T star x to D inverse. So therefore, we have a map T star x, tensor T star x, to D minus 2. And therefore, we have a map from two forms, wedge star of T star x to D minus 2. But we also had an embedding of D minus 2 into T star x. Let's call this one Q and this one I. So something which is unfamiliar in geometry is that there's a map from two forms to one forms. Okay. It doesn't exist. We don't usually meet maps from totally generic maps from two forms to one forms. But here it is. It's a consequence of this exact sequence. I can't hear you.
How do we know the Q is not 0? Couldn't it be the symmetric?
Well, if you calculate in local coordinates, you'll see that Q isn't 0. So the map here, phi mapped d theta to d theta. And it mapped dz to theta d theta. So Q of dz d theta is theta times d theta squared. But more trivially, Q of d theta is just d theta squared.
commutative. You have wedge 2.
Well, we have to remember that wedge 2
which
is skew symmetric in the Z2 graded sense.
Yes, sir.
So d theta, wedge d theta is not 0, precisely because it's commutative. As you say. So this mapped 2 forms to 1 forms in general, but now there's some magic, which I considered showing on the blackboard, but I was afraid it would get to be a little bit too long. But you prove by purely local calculation that if d theta is 0, then theta is d of I composed with q of theta. So that shows that a closed holomorphic 2 form is exact. Namely, there's a completely canonical thing that it's d of. So
Between the Fulham complex and this O2 closed form.
are you telling me or asking me? If you're telling me, I'm sure the answer is yes. Oh, okay.
Yes.
So say that again?
That one has 2 complex, the third one with closed form and the long one, and they're canonically homotopic.
What would you mean by the short one? You stop after one form?
O going to closed one form.
Okay.
And it's containing the big one and the
I see. You're saying that D, the big one meaning forms of all degrees.
yes.
I see. So if a 1 form is closed,
Yes, you know that they have the same cohomology. You
Yes.
have the Poincaré lemma for those.
yes.
And so it's not so surprising that they are even homotopic. This further.
Okay. Thank you. I'll try to understand it better, but maybe I can't. Well, trying to worry about what to say next. Are there other questions? So I'm sure it's something like that should be right, because to me it's just a miraculous formula without exactly knowing what to say about it, except that you can use it in this proof.
Is D anti-commutator I composed with Q equal to 1? Does that make sense?
It makes sense, but I doubt it will turn out to be true. I think this is the only thing that's true. I'm not. Oh, sorry. No, I'm not totally. Well,
Apply this immediately, right?
okay. No, I don't know. So you can give that one a go. I don't know for sure. This is as far as RS and B got, and I think I slightly streamlined their explanation, but I don't think. Okay, I don't know the answer to your question. Okay. I think we have to resist the temptation to say more on super Riemann surfaces, because I want to talk about string theory. So.
Second Riemann identity.
What is the second Riemann identity?
The genetic product.
The matrix is positive that way.
Well, trivially there is, because you see, if the odd parameters are 0, the superperiod matrix reduces to the classical one, whose imaginary part is positive. And turning on infinitesimal parameters won't affect a question of positivity. Now, I want to head for an explanation of space-time supersymmetry. But first I have to say where we integrate in string theory. So we've heard about the moduli space of super Riemann surfaces. I won't always write the super, but I'm emphasizing it now, with n the Schwartz punctures and r Riemann punctures. There actually are 2 cases that I'll explain a little bit briefly. They correspond to heterotic and type 2. So in the heterotic string, what I'm about to say was kind of said by Doker and possibly by Donaghy this morning. But we work inside the product of the moduli space of super Riemann surfaces with what I'll call the complex conjugate of the ordinary moduli space. So I need to emulate Ron and have a different font for the ordinary moduli space of Riemann surfaces. So what I mean by complex conjugate, if you like, is that this parameterizes complex structures on the same topological surface but taken with opposite orientation. Maybe we'll write a prime. The prime indicates complex conjugation. We might want to compactify both of these, but my explanation at the moment will be too rough to take that into account. So, okay. What we integrate over isn't going to be the moduli space of super Riemann surfaces. It can't be. Well, we'd have to know what was meant by smooth functions over there to have a hope of defining anything there we might integrate. And string perturbation theory generates smooth functions. But if you try to think that they're functions just on M, G, and R, you'll run into some contradictions. A more accurate explanation is the following. You take the product of M super with M prime, the complex conjugate of the ordinary moduli space. And you're going to, roughly speaking, work close to the diagonal in that space. Where what close to the diagonal means, there's a real variety delta in M prime times the reduced space of the other. This one parameterizes a Riemann surface. This one, the bar means opposite complex structure. This one parameterizes a Riemann surface with spin structure. What I would mean by the diagonal is that if we forget the spin structure, those two Riemann surfaces are complex conjugates.
Don't give a spin structure.
No. And then, actually, sorry, I forgot the G and R. And here it's just G and N plus R. So there is such a delta, which is a real variety. And then we thicken delta in a way I explained yesterday to what I'll call the integration cycle, gamma, G, and R, inside the product. I explained this thickening yesterday. Remember I said that for every real submanifold of the reduced space, you can thicken it slightly in the odd directions to get something that has the same odd dimension as the total space and whose reduced space is what you started with. And there isn't a canonical way to do this, but as long as you are integrating closed forms, the precise way to do it doesn't matter. Now, I should say that none of these spaces are compact. And we need more care near infinity. But I won't say anything about that today, and I possibly won't even have time later. At least I will explain some of the subtleties at infinity, but I probably won't give a complete explanation. But there are reasonable conditions you should place about exactly what you do at infinity. But knowing what those conditions are depends upon having the Deligne-Mumford compactification of the supermoduli space as well as the ordinary one. Not just the ordinary one. Knowing about the classical compactification would not be enough. So what you're hearing in Deligne's lectures about compactification of the supermoduli space is necessary to be able to define gamma properly at infinity. Then string perturbation theory generates typically, okay, I'll go into more detail in a moment, but it generates typically an integral form, omega of top degree, and then we calculate the integral over gamma G and R of omega. I'll go into more detail about that in a moment. I do want to mention the other case of type 2. So type 2 means that we start with Well, M super, we start with the product of two copies of M super. I'm calling them M super and M super prime, where the prime just means that we think of M super prime as describing super Riemann surface structures with the opposite orientation. But they have different numbers of Riemann and Neveu-Schwarz punctures with only the condition that the sums are equal. And of course, R prime and R are congruent to 0 mod 2 for topological reasons, as Denagi has explained. So if you ignore the details of the supergeometry, you'd say that you have a Riemann surface that has both a peculiar holomorphic and anti-holomorphic structures. It has punctures. Each puncture has a pair of labels. So a puncture might be of type Neveu-Schwarz in both structures, or it might be of Riemann type in both structures, or it might be of one of the two mixed types. No, in type 2, a puncture is a puncture in the super Riemann surface structure of the right movers, of the holomorphic degrees of freedom. It's also a puncture in the super Riemann surface structure of the left movers. Sorry. For this to completely make sense, I should specify in what sense we're working near the diagonal, which I'll do in a second. So I'm afraid in saying this, I jumped slightly ahead. So if we were simply working on the product of the two moduli spaces, there'd be no relationship between one set of punctures and the other. And it wouldn't make sense to say that the same puncture has a pair of labels. Rather, we look at the reduced space. So M prime reduced times M reduced parametrizes a pair of sigma with a spin structure and sigma prime with a spin structure. And we define delta by saying that sigma prime is the complex conjugate of sigma with the spin structures forgotten. Sigma prime is the complex conjugate of sigma in a way that respects the punctures. So sigma prime with its punctures is the complex conjugate of sigma with its punctures, with no claimed connection or assumed connection between the spin structures. So having said that, now it makes sense to say what I said before, that a puncture has two interpretations in terms of the holomorphic or the anti-holomorphic complex structure, and therefore there are four possible labels for a puncture. Now, this business of forgetting spin structures and so on will undoubtedly sound rather bizarre if you're not a string theorist. And part of the purpose of the rest of today's lecture is to explain why it's necessary. But I want to, in doing that, just to make it less clumsy, I'm going to concentrate on the heterotic string, where there's slightly less to say. So as in Doker's talk, in general, points are labeled by vertex operators. So let's say V1 up to Vn. So in Doker's last lecture, he assumed that all four vertex operators, well, first of all, he considered only the case where there were four particles, and he assumed that all four vertex operators corresponded to a graviton. So he considered a scattering amplitude with four incoming or outgoing gravitons in asymptotically flat spacetime. In general, though, we have any number of incoming and outgoing particles, and they're all described by vertex operators, and each puncture is labeled by a vertex operator. There are vertex operators of Neveu-Schwarz or Riemann type. And in type 2, there are four types of vertex operators because they each have come in two types. And then for any set, we find from the path integral an integral form of top degree, a volume form, omega that depends on this set of vertex operators. And then the scattering amplitude is the integral over the cycle However, these integral forms have a very delicate behavior near infinity, and the integrals are in danger of not converging. So I will give an introduction to the behavior near infinity tomorrow when we talk about the super-Mumford form and its consequences. But for today, let's just say that this is in great danger. You can define perfectly good volume forms, but they're in great danger of not being able to integrate them. And in practice, to be able to integrate them requires space-time supersymmetry. We need space-time supersymmetry to make the theory work. So what does space-time supersymmetry mean? First of all, the V's that we use when we calculate a scattering amplitude are neither holomorphic nor anti-holomorphic. That means when we work near the diagonal in the product of a supermoduli space and another moduli space, V does not come from either one of the two. But there are exceptional cases. There are exceptional holomorphic vertex operators that were introduced by Friedan, Martinic, and Schenker in the mid-'80s. And they generate the ones, we'll discuss the most interesting ones, the ones that generate space-time supersymmetry. So there are 16 of them that transform in a spinor representation of SO19. The Lorentz group in 10 dimensions let me speak more slowly. For brevity, I will only describe this for strings in R in 10-dimensional Minkowski spacetime. Then the Lorentz group is SO19, and there are supersymmetry generators that transform in a spinor representation of SO19. And we'll take a generic linear combination. We'll just take a linear combination. Well, I'll present the lecture as if we're just picking one such operator. So this is only Ramon. This is Ramon only. I'm actually going to write this linear combination with a more fancy symbol that suggests to me more an operator. So Q is associated to a Ramon puncture. And moreover, it's holomorphic. What does holomorphic mean? Well, we can modify slightly what I've said. So inside M super, I'm going to call the number of Ramon punctures R plus 1. There are for particles we're scattering, and there will be one more for this exceptional operator. On the other side, we'll just take the ordinary moduli space with N plus R only. And in there, we define delta by saying only on the reduced space, one surface is the complex conjugate of the other, and all of these punctures except the exceptional one match up with these. So that condition defines a bosonic manifold in the reduced space, and we thicken it to gamma. This is a slightly exceptional gamma. I'll call it gamma Q, just as a reminder that one of the operators is Q.
R here to be odd?
Yes.
Odd so that R is even?
Yes.
Okay.
I I just wanted to make sure I understand the odd directions there. So when you say that a Ramon puncture matches a Schwartz puncture,
Yes.
or one of them is a point and the other is a
It
subvariety,
doesn't matter because
you mean inclusion.
when we construct a subvariety of a complex supermanifold, we don't, well, when we're doing something, we've got a closed integral form that we're going to integrate on a cycle. We only care about the cycle up to homology. And so we don't have to be so literal-minded as you're suggesting. But in any case, I defined delta on the reduced space. So there wasn't even a divisor. And then we thickened it. I didn't tell you how to thicken it.
Directions above.
We take all the odd directions above it, and we don't care precisely about how we do it. We just do it in some non-degenerate fashion.
Right, but the consequence of that is that if you have two Schwartz functions, they don't have to be at the same point. They can differ by an odd direction.
Well, you see, that's not a well-defined statement. So we can't say that if the supermoduli space of super-Riemann surfaces were split, I would have been able to skip a few things I told you. But it's not. So I had to give more circumlocutions. I considered omitting some of them on the grounds that unless you really get deep into the woods in this subject, most people wouldn't care about them. But I felt I should show you one can make correct statements. The only trouble is that it's hard to make correct statements that are brief and also make them completely understood. So you're asking about a lot of details that are kind of irrelevant because of the fact that the odd directions never contribute anything in any statement of a topological favor. Any other questions?
In physics language, are you inserting a zero momentum dilatino, or?
I'm inserting what was called the supersymmetry, the vertex operator.
That's a current, right? I mean,
You see, the way I said it was that it's holomorphic. You expressed it by saying that it's a current. I'm about to tell you something that I think will make you happy. In other words, I'm about to tell you something which I hope you'll recognize as a slightly improved version of whatever you were aiming to say. So, I apologize if that sounds flippant. Sorry. I think it's better if we get a little bit. I think it's better, Greg, if you ask questions after I've gotten a little bit farther. I've drawn the picture, but now I'm not distinguishing between the Schwartz and Ramon vertex operators in the way I draw it. There's one exceptional vertex operator that I've called curly Q. That's the one which is holomorphic, which you express by saying it's a current. And the other ones are the generic vertex operators. Now we do the superstring path integral, but it generates a codimension 1 closed integral form. So the statement that says codimension 1 is what you were capturing or getting at by saying that it was a current. When you said it was a current, you meant it was a 0-1 form instead of a 1-1 form. But see, that formulation would work better if both supermanifolds were split. So I haven't used that formulation. So a version of what we're getting at, is that this does not generate a top form. The missing index, the gap that you felt, which led to your question, is manifested in the fact that we generate not a top form, but a codimension 1 form on the integration cycle, but of course, well, it's really defined close to the diagonal in the sense I explained in the product of M prime with M super. But in particular, it's defined on the integration cycle. Now, we have to think, okay. So what can we do with the closed differential form of codimension 1? Well, we can act with D on it so that it becomes of top degree, and then we can integrate it. But of course, we'll get 0 because I told you it was closed. But we have to be careful here because the integration cycle is not compact. and there's going to be a tricky behavior at infinity. So we should really cut off a little bit the integration cycle near infinity. And there are many components at infinity, as you heard about a little bit from Donagi. So we cut off gamma slightly near each boundary component, which we do using some knowledge of what the boundary behavior looks like. And then we write just schematically, we write the boundary as a union of boundary components that I'll call partial I of gamma. So then the formula we get is that 0 is the sum over all boundary components of the integral over partial I of gamma of this form. So we get a relation involving a sum of a lot of boundary components. And that leads to an identity that's called space-time supersymmetry, but it has the following properties. So I'm going to draw 3 pictures. They differ by how many other vertex operators. So, okay. Well, maybe I should draw 4 pictures. I'll draw a non-separating degeneration. And then I've drawn a separating degeneration which has Q on the same side as some more vertex operators, and one where Q is on the same side with one other vertex operator, and finally one where it's on the same side as no other vertex operators. So with a little knowledge of what is happening at infinity, you can show that a lot of contributions vanish. So for example, the separating contributions go to 0. Universally. Also, contributions with more than one operator on the same side as Q go to 0 universally. The one with Q on only one side and not the other is 0 in R10 and lots of other models. In some sense, it's 0 usually, but is an obstruction to the theory. When that contribution is non-zero, physicists would say that supersymmetry is spontaneously broken, and then in higher genus, the theory won't work. A mathematician, since there isn't much time, I might briefly say it's analogous to a Maurer-Catan equation or something not being satisfied that you needed in order to define a theory.
The genus 1 component where Q is 1?
Well, I drew it as a genus 1 component. It has to be a stable curve, so it can't have genus 0.
Right.
And it turns out that there are non-trivial examples which actually partly motivated the examples Donagi was explaining at the end of his lecture today, where precisely with the genus 1 component, this contribution is non-zero. So there's a real obstruction. Yes?
The picture you give only general bound at infinity, but in fact all those diverge or
Yes.
intersect. And
Yes. I don't think it leads to... So for example, these two are so robustly 0 that...
But the interesting one you have to
The interesting one is here.
infinity.
The interesting one is here, but you see, well, I'm about to tell you something about it which will make it clear what we should do.
We're integrating a codimension 1 form, so we don't care about further degenerations, right?
Well, we have to be a little bit careful in a statement like that because of the fact that the divisors at infinity intersect. But for this particular problem, I think that nothing happens that changes the picture as a result of those intersections. But you see, something very nice happens to this one. You can show that, first of all, this does make a contribution at infinity. And there's a linear transformation which I'll call Q of vertex operators. So I'll write it as V going to Q of V, such that this picture can be replaced with the same picture with the component containing Q contracted. And then there's one more puncture on this side, which is labeled by Q of VI. So I draw the same picture again, but without the component on the left. And here I put Q of VI. And whatever other vertex operators were there are still there. So to recapitulate, there are a lot of components that won't contribute. And the theory will only, there's one dangerous component, and the theory will only work if that doesn't contribute. But
Piece on the left, or does it?
well, it makes a non-trivial contribution with genus 0, and there may or may not be corrections in higher genus. It's definitely non-zero in genus 0. It's non-zero in genus 0, and there's a simple formula for it. This is a reinterpretation of something computed by Friedan, Martinek, and Schenker in the 80s. So I drew it as genus 0 because that's the basic contribution. But here I drew genus 1 because that's the lowest case, and also there are non-trivial examples where it contributes.
So V1 had to be Ramon, but this new one is Noah Schwartz, is that right?
V is of any type. And since, you see, let's just look at this guy.
Q is
I know, but I'm losing one.
Q is of Ramon type. I didn't say what type V was.
well, Q of V is the opposite of whatever it was.
I'm about to explain why, though.
I see.
So Q is of Ramon type, V is of some type. But you see, this third puncture is of the opposite type from V, because the number of Ramon punctures will have to be even.
Right, okay.
And whatever type it is on this side, it's the same type on the other side. So Q of V is of opposite type from V. So this is a map. The map Q exchanges Neveu-Schwartz and Ramon states. Sorry. I think I just covered our identity. So our identity was that the sum over all boundary components vanishes. But when the obstruction vanishes, that can be reduced to a simpler statement. There's one boundary component contributing for each one of the V's, and it's obtained by just forgetting the Q and replacing V with Q of V. So the identity is well, so there's a linear transformation of vertex operators, which if we apply it to all the vertex operators, leaves the correlation functions invariant. This type of statement would merely possibly be more, the bosonic analog of such a statement might be more familiar. Suppose it were the case, okay, instead of Q, let's talk about P, which might be the energy, for example, and then P of VI with the lambda I VI, let's say, except it would usually be called PI. If it were a bosonic operator, we would diagonalize it. And then an analogous statement would tell us what? Well, you see, when you replace V by Q of V, that would multiply by P. So the analogous bosonic statement would be that the sum of PI is 0, or else, well, let me write it in full. If the V's were eigenstates of Q with eigenvalue P, the identity would become that the sum of PI times the same thing with no Q is 0. So then you'd say that either the sum of the P's is 0 or the correlation function is 0. That's usually called a conservation law. The scattering amplitude vanishes unless the sums of the charges of the operators is 0. What we've proved is the supersymmetric analog of that, except that it's unnatural to diagonalize Q. We could if we wanted to, but it would feel ugly. So, but this is the identity you should expect in a theory in which a transformation of vertex operators by V to V plus epsilon times Q of V, where epsilon is an odd constant, is a supergroup of symmetries. In other words, we've discovered a supergroup of symmetries of superstring theory, which is actually why it's called superstring theory. It's not called superstring theory because of the super Riemann surfaces, It's called superstring theory because of the space-time supersymmetry. If we're physicists, we're very happy now.
What about those obstructions?
Well, in any given model, you have to prove the obstruction vanishes. And in practice, it's pretty easy to decide if it vanishes in a given case. So it's a non-trivial obstruction. Some models do have this obstruction. When the obstruction's 0, it's usually true for elementary reasons.
Is there an independent obstruction at every genus, or is it just that one
Well,
piece?
there's an independent obstruction at every genus in principle. But in compactification to 4 dimensions, you can show that if it vanishes in genus 1, it vanishes in higher orders. In compactification below 4 dimensions, I don't expect that. But it will be hard to find non-trivial examples. The reason is simply that it's very hard to have the obstruction vanish in genus 1 unless there's such a good reason for it to vanish that it will vanish in higher orders. But although I don't know an example, I would expect in compactification to 3 dimensions that you could find a case, if you were powerful enough,
It might vanish.
where you'd have to go up to genus 2.
I see.
I don't know for certain. But there's nothing I know in the general theory that would tell you that you're finished after genus 1. You need to use some facts about a particular theory. I might say it's actually rather tricky to analyze this obstruction. So I found it to be hard work to translate the physics question into a question about super-Riemann surfaces. And then Rondinaki and I found it to be non-trivial to answer the question on super-Riemann surfaces. So it's kind of hard work. But anyway, there is that obstruction, and you want it to vanish to make the theory work. So there are lots more fun things to say, but maybe we should have the discipline to wait till tomorrow. Yes, Greg?
Going back to the type 2, there are 2 types of type 2. Is that a difference in the cycle?
So Greg is saying that there's 2 types of type 2 superstring theories. So it has to do with the fact that the moduli space of super-Riemann surfaces has 2 components, and even in odd spin structures. And I defined an integration cycle in the product of m times m prime, so there were 4 choices. But if you're more careful, you have to include those with signs. And the 2 differ by the sign of the contribution of the component with odd spin structure. And any other questions?
Let's try it again.